Cashmore. I'm going to be presenting partially grounded planning with quantified Boolean formula, which is a work I did with Maria Fox at King's College. The idea for this is to translate planning problems into Boolean formula without first grounding. The motivation for this is so that the resultant formula will be very small. The size and memory during solving will be much smaller, and as a result we'll be able to scale to problems which are much larger and have many more objects of the same object type. When planning in SAT, generally the variables represent parts of the planning problem in a very intuitive way. We have Boolean variables that represent the Boolean variables that represent fluids in the domain and whether or not you take an action at a specific time step. And we wanted this encoding to also be intuitive in that manner and to make plan extraction very easy at the end. Okay. QBF extends SAT to include these universal quantification layer beforehand. If you imagine the SAT formula is a collection of Boolean variables, and we say that we assign as an assignment to these variables, true or false, such that the following formula has been satisfied. In QBF, we will say that there exists an assignment to A and B in this first formula here, such that for any assignment to Boolean variable C, there exists an assignment to D such that the formula is satisfied. So in this way we have a branch in formula to create two sub-formula that both must be satisfied, one in the case where C is true and one in the case where C is false. So in the second example here, we'll say that for any assignment to C, there exists an assignment to D such that this formula is satisfied. In this case, the formula can be satisfied. When C is true, D can be true, and when C is false, D can be false. And that satisfies the formula. So we want to exploit this expressivity, and we do it in the obvious way. Our SAT formula is, we want to say there's an assignment to all these Boolean variables which represent part of the plan, such that the formula is satisfied. That is, there is a plan. So what we're going to say now is that for any occurrence of an object of this non-grounded type, there exists an assignment to the variables that represent this object, such that there exists a plan. Okay, that's the end of the formula, so the rest of those pictures. This is a simple encoding using SAT here to work as an example. We have two pigeons and two empty boxes, and we want to put the pigeons into the boxes because that's what you do with pigeons. Each of these boxes on the slide here represents our Boolean variable. This being SAT, they're all existential variables. So we'll say that there exists an assignment true and false to each of these, such that the formula is satisfied. The formula itself, all the constraints are invisible right now, but they're pretty obvious. The actions imply their preconditions, so this place one pigeon implies that the pigeon hasn't already been placed. And the facts imply a disjunction of the actions which achieve them. So here's an example initial state where box 1 is empty and neither of the pigeons have been placed in the box, and our goal is that we place the first pigeon into a box. And that's a pretty obvious solution there. We just choose to place the pigeon into the empty box. You can see this SAT problem here has split the actions into two parts. So instead of saying we're placing pigeon in box, we have two variables, one for placing the pigeon and one for placing the box. This is just the simply split representation that was introduced by ICAPS and Solomon in one of the first papers, and there are more advanced and better ways of doing this, but I'll talk about that later. So the grounded formula, in this case, would have a number of variables inside the formula in the order of the product of pigeons and boxes. If we reduce it, then that reduces to the number of pigeons plus the number of boxes. But we can do better than this in QBA. So it's the exact same problem, but now we're going to need pigeons ungrounded. We have a set of existential variables there representing the boxes. Then we have a single universal variable, which is sort of saying for any pigeon, there exists an assignment to the following variables representing that pigeon, such that the formula is satisfied. Since there's a single universal variable there, there will be two sub-formula, one for each of the pigeons, pigeon 1 and pigeon 2. And we've dropped the parameters from the existential variables at the bottom now, because those variables refer to all of the pigeons. One problem we have now, though, is that if we say place 1 is true, and we're putting the first pigeon into the first box, same as before, there's nothing to stop us putting the second pigeon into the first box at the same time. And we don't want that to happen because that's impossible. So we need to make those two actions mutually exclusive, which we can't do with a simple constraint, since they're the same variables just in different contexts. So we introduce a lock variable here. This variable, it just locks the parameter of this action place 1. And it does this by forcing the lock variable to be equal to the universal variable A. So, in an example, here's the same initial state as before, except this time both boxes are empty. And this is the first pigeon, because we're looking at the formula when A has been set to 2. And the pigeon hasn't been placed, and we want to place it. Here's the other half of the initial state. When the universal variable is false, we're looking at the second pigeon, and he's also not been placed, but we don't care about it. I'll get back to the first part. This will satisfy the goal. We've decided to place the pigeon, and because of that, the lock variable has been forced to be equal to the universal variable. That's effectively bound this first pigeon in as the parameter of this action place 1, and we've put him into the first box again. If we look at the other pigeon, because the lock is now different to the universal variable, the action has been forced to be false. So we've effectively made the two actions mutually exclusive with the use of this extra variable. And that's our solution. So now, with the pigeons left ungrounded, the size of the formula of variables and constraints is now of the order log number of pigeons plus the number of boxes. The reason it's log is because we have to have a number of log variables equal to the number of universal variables. And the number of pigeons is going to be 2 to the power of the number of universal variables here. And here we've now left them both ungrounded. So this is the best. We've included a new action at the top there, just to act as the operator in this case, since now both parts of the action have been left ungrounded. We've got a new lock variable, and that one is obviously the parameter of the box part of the place action. So the initial state is before. We want to place this first pigeon, and the first box is empty. So we decide to place the pigeon into a box, we don't know which box yet, and that forces the lock variable to be equal to the universal, first pigeon. Now we look at the second pigeon and the second box, since now the universal variable is false. And since the lock on place 1 is different from the universal variable, we know we cannot place the second pigeon. And we decide to place the pigeon into the second box this time, which means that box is now no longer empty, and its lock has been forced to be equal to the universal variable. Looking back at the other side, because of that, we can't place the first pigeon into the second box as well as the first box. Okay, so this fully lifted, we've now logarithmically reduced the size of the formula completely. Before I just talk about the results, how long do I have? 5 minutes, 10 minutes? Okay. Good. There's a couple of things I've glossed over here. First, the most obvious one is, what if we want to put the first pigeon into the first box and the second pigeon into the second box at the same time? And at the moment, you would need 2 place actions. You'd need a number of place actions, a number of times you wanted to do this in parallel. And this is just a consequence of the way we split our parameters. I said before, we're using the simply split formalism, which is quite old now, and it only allows for partial parallelism in the encoding. There are alternatives such as Robinson's splitting on ground conditions from 2009, which will allow us to go back into proper parallel plans, or using a SAS plus encoding, which I'll talk about later again. Also not included in that problem was a fluent, which included multiple parameters of ungrounded types, for example, pigeon in box. In this case, you really want to remember which parts of these split propositions belong to the other part. So this is just unusual locks as well. The details are in the paper, but it's no more complicated than the action locks. Okay, now the results. We tested on 3 domains which involve lots and lots of objects at the same time. We used the SAT encoding that we did in SAT 506, which is facts and actions. We did this because it's the same state representation that we're using in our QBF formula. There are other representations, better representations, all sorts of clever tricks you can put into the encoding and into the solver to improve performance, and these are all applicable to the QBF case as well. So we've just used 2 very simple encodings that we could compare to each other. We solved the SAT encodings using picosat and the QBF encodings using Quantified. We use picosat since it's the solver that's used internally within Quantified, the same version. Okay. So this is just a pigeonhole problem I showed before, a very simple problem. But as you can see, as we started to increase the number of pigeons, we began to struggle to even encode the problem in SAT. We were using a computer with 8 gigabytes of memory, and I gave it 2 hours to encode and solve the problem. And in the end, we managed to encode and solve a problem that we couldn't even encode in the first place in SAT. These are the gripper problems. There's a robot, and there's a big mass of balls that the robot wants to pick up and move to another room somewhere. Here, we don't scale as well as we did in the previous problem. The reason being, now the size of the domain isn't a product of the number of ungrounded objects, since the action to pick up a ball and put it back down again only has 1 parameter. However, we still make an improvement for both encoding time and a little bit of solving time. That's a little bit. Now finally, blocks world. This is a great problem for us since it includes these fluents with multiple unbounded parameters. You want to remember which block is on which other block. And we again were able to encode and then solve a problem that we couldn't even encode, in SAT. Okay, so for future work, we'd like to obviously investigate with smarter ways of splitting the action so that we can return to having parallel plans, and then perhaps try to include some of the other advantages that state-of-the-art SAT encodings have. An alternative to the Robinson's split action representation is a SAS plus representation, which works very well since there are 2 layers to it, where they have the action layer and then a transition layer where they describe the DTGs of the problem. And these layers seem to correspond almost exactly with the 2 existential layers we have in our problem, the grounded and then the ungrounded part. So we simply represent these DTGs once per object type, and we get some good results there. And finally, we'd like to combine it with some of our other QBF encodings, ones which are logarithmic in terms of number of time steps. In this work, we've reduced the width of the problem, so to speak, and we could also reduce the length, and we end up with a very tiny formula at the end of it, which could be a good thing. Okay, so in conclusion, we have an encoding to QBF rather than to SAT, which performs better on problems in which there are a lot of objects at the same time. And if there are no candidates, so you should note that if there are no candidates for leaving ungrounded, and your domain just has a few objects of each type, then the problem would resemble exactly the SAT problem anyway, and you would never lose.